Okay, so today we are going to continue talking about intersection theory, but we need one more preliminary, which is the theory of oriented manifolds. So we're going to talk about orientations of manifolds. So I'm going to go a little bit quick because I think you've seen this before. Anyway, so first of all, we have to talk about an orientation of a vector space. So let V be a vector space. We can define an equivalence relation on the set of bases of V as follows. So we say that two bases, V1, Vn, the base V1, Vn is equivalent to the basis W1, Wn if the linear transformation that takes Vj to Wj, so this is an isomorphism of V, goes from V to V, has positive determinant. Okay, so let me just recall that the determinant is defined for maps of a vector space to itself. You don't need to choose a basis and define it for a matrix. Yeah. So that and it's easy to check that this is a equivalence relation. So an orientation. Well, let me just remark that there are exactly two equivalence relations. Exactly two such equivalence relations. Okay, so definition, an orientation of V is a choice of such an equivalence relation. And if V is oriented, if a choice is made, V is said to be oriented. And a basis in this equivalence class is called an oriented basis. So a choice of orientations of a vector space, another way to say is basically you throw away half of the bases and you keep the other half. Okay? And clearly, if you have a basis, if this is not oriented, then there are a bunch of ways to transform this into an oriented basis. One of them is to just change the sign of the last one. This is oriented. Maybe this is an observation. Another way is to switch the order of two of them. So if you just switch V2 with V1, and then you keep the other ones, this is also oriented. Okay, any odd permutation will do that. Or if you change the sign, an odd number of signs. Okay. Well, this is linear algebra, but are there any questions? Maybe someone has never seen this.
Just to remark, there are
Yes.
exactly two equivalent classes.
Yes.
Okay.
They're exactly two equivalents. Oh, did I say relations? I meant classes. They're exactly two such equivalence classes. Yeah. So because, if you take two bases and you look at the change of variables, this linear transformation either has positive determinant or negative determinant. And the product of two linear transformations, the composition of two linear transformations with negative determinant has positive determinant, because the determinant of the composition is the product of the determinants. So that's why it has. I mean, if you've never seen this before, maybe it's worth saying this is an exercise. But maybe if you've seen this before, this is probably straightforward. Okay. Other questions? I can't do a show of hands so easily as I could do in person. How many of you have seen this before? How many have not? But I think most of you, I would imagine most of you have seen this before. Otherwise, please stop me. Otherwise, if you don't stop me, I'm going to continue going fast. Okay, so now we can talk about an orientation on a manifold. So let X be a smooth manifold. So I'm not going to talk about orientations on topological manifolds because it's a little bit more subtle. But on smooth manifolds, it's a little bit easier. If you want to know about orientations on topological manifolds, you should take algebraic topology next semester. An orientation on X is a choice of orientations of TPX for each P in X. So you orient, you choose an orientation for all the tangent spaces. So these are all vector spaces. But you don't want to do that in a random way. You want that to be somewhat reasonable. So what you require is that for each chart, for every chart, P, x1 to xn, that goes from U to Rn, you have that either ddx1, ddxn is oriented for every P in U, or it is not oriented for every P in U. Okay. This is just a condition of to say that this choice of orientation is moving smoothly, or is around any point. I mean, it's actually just a continuous because the two equivalence classes are disconnected. Then you only really need to require continuity. So an equivalent way of saying this is that near P, we can choose continuous vector fields V1 up to Vn, such that V1 of P, Vn of P is an oriented basis of T V1 of X, an oriented basis of Tx of X for every X. Okay, so that basically is saying if you have your manifold and you choose one orientation, say you choose this one first and this one next, this actually induces an orientation locally nearby. Okay, so for all the tangent spaces nearby. Is that clear? Is the definition clear? I mean, what I don't want is, like, I don't want a random choice at every point. Like, I don't want this choice to, like, be a discontinuous function. That's all we're requiring. Okay, so how do we find an orientation? Well, as I said before, if you want this condition to hold, then actually what you have to do, if your manifold is connected, what you have to do is you choose a point and you pick one orientation for the tangent space of that point. So you choose one oriented basis. You choose a basis, say this is V1, this is V2, and that gives you, this is V3. You choose an order. And when you write the set like this, it's an ordered set. So you can't switch the order. I mean, switching the order changes the basis. It's a slight abuse of notation that people usually do in linear algebra. So when you pick this oriented basis, now this is going to induce an orientation in all the tangent spaces sufficiently close to P. So if you take the domain of a chart, this induces an orientation in all Txx for every x in U. And if a manifold, if X is connected, then any 2 points you can connect through a finite set of charts. If the manifold is connected, then it's connected by path, so you can find a path from P to Q, and then you can cover the path with a finite number of charts, because the path is compact. So you can apply this game, and that means that you're going to induce an orientation at every point. Okay, so then does this imply that every manifold is orientable? So can you find an orientation on every manifold? This is not a rhetoric question. It's a question for you to reply.
No, you cannot find. You need connectedness.
You need what?
Connectedness.
Yeah, but if you're a connected manifold, can you always find an orientation? Can you see another problem?
You need
So what
to look.
I don't remember the reason, but the band, a faixa de Mabels, and cannot be oriented.
Yeah, so can you see what goes wrong in this argument? So what I'm saying is, if you fix an orientation at a point, a tangent space of a point, which we can always do, then you can use a path to transport this orientation to every point in the manifold, if it's connected.
Porque outro caminho pode dar outra orientação no final.
Exatamente. Yeah. So that's the problem. Like, I have a path from P to Q. If I choose another path, that will I can, choose another set of charts. And then I'm going to orient, I'm going to get an orientation on the tangent space at Q. And there's nothing that guarantees these two are the same. Okay? So that's the problem. The problem is that this way of doing it is not necessarily the same. And here, maybe I'm going to state an exercise, which is a very cute little exercise to make sure you're understanding what's going on, which is that if X is connected and simply connected, then X is orientable. Simply connected just means that every loop is contractible. So, I mean, the idea, it's pretty easy. It's pretty simple. So if you have two paths like that, if the manifold is simply connected, that means that this circle, that that you get, this closed path that you get when you go from P to Q using one path and then from Q to P using the other path, this bounds a disk. This is contractible. So then you can actually fill in the disk with charts. And using this property, you actually can prove that the orientation that you get through this path is the same as the orientation that you get through the other path. Okay, so I'll leave the details for you to fill in. Okay. But yeah, as someone said, let's talk about non-examples. I guess maybe that's the interesting thing, because we already see from this exercise that there are a lot of examples. But non-examples. I guess the most famous one is the Möbius strip. So. And it's actually a nice one to see exactly where this construction fails. Okay, I'm not a great drawer, but I think everybody knows the Möbius strip. And as you've probably seen a lot of times, the problem is if you take a point here and you look at a path that goes here, and then you basically take two paths, this path and this path, and say you fix an oriented basis, this oriented basis like this. When you move it all the way here, then along this path, then this will give you this basis, and then when you move it along the other path, it will give you this basis, something like that. Yes, that's right. So you see that these two bases, they're different. They're not in the same equivalence class at this point, Q. Another way to say it's a kind of equivalent is you can just take a closed loop, and then you can take the bases and move it around the loop and see how it gets back. And if it gets back with this in the same equivalence class, then there's no problem. But if it gets back in the opposite equivalence class, then you cannot orient that manifold. Okay, so this means this is not orientable. And I mean, I'll talk about these kinds of examples more of surfaces later on after we talk about Morse theory. But if you take two Möbius strips and you glue them together, I mean, I think you've seen the Möbius strip before, and the Möbius strip is kind of a nice little manifold, and it has the property that the boundary of the Möbius strip is a circle. So now what you could do is the construction that I said before, where you can just glue a manifold to itself along its boundary. Okay, so let me write it like this. Union. And this just means you take x times x, x disjoint union with x, and then you glue, so you quotient by some equivalence relation, and the equivalence relation is you say that x is equivalent to I if x, let me write it. You just glue the boundary. So you take the points here, they're on the boundary, and you glue to the points here, they're in the boundary. Okay, I'm not going to write this down, but you take two of the same and then you kind of glue them together. And the point is when you do that, you get something called the Klein bottle. And since x is already non-orientable, then this is also non-orientable. And the Klein bottle is nice because now it doesn't have boundary. Because the boundary of x and the boundary of x, you glue them together, so you no longer have boundary. The Klein bottle is an example of a boundary less non-orientable surface. But I'll talk about these examples a lot more in depth when we classify all the surfaces. Okay. Well, let me be not so sloppy and write down, because maybe if you haven't seen this, this is a little it's a little hard to understand. So let me not be lazy and write down what the Klein bottle is. So the Klein bottle is the following thing. So let x equals y equals the Möbius strip. And we can define the following object. So it's x, this joint union with y, quotiented by an equivalence relation. Quotiented by the equivalence relation just means that we identify, so this means the equivalence relation is, you say that x is equivalent to y. Oh, so since x and y are the same, then we have sort of an obvious diffeomorphism, like the identity diffeomorphism from x to y. So we say that x equals y if phi of x equals y. Okay, so the idea is sort of, this is your Möbius band, this is the other Möbius band, so this is x, this is y, and you just glue the red to the red, like that. And then you end up, when you do that, you end up with K, with the Klein bottle.
The diffeomorphism is only defined on the boundary, right?
What?
The diffeomorphism is only defined on the boundaries, because if you are gluing the end.
Sorry. Yeah, yeah, you're right. Sorry, I want to just define the diffeomorphism on the boundary. And this is just the identity diffeomorphism. Yeah, maybe. Sorry, I can write something even. This is what happens when you improvise. You can just say the following. So you say that x is equivalent to y if x and y, well, if x is equal to y. If f is equal to y and f is on the boundary. F is equal to y, f is on the boundary of x. There we go. Yeah, the problem is that really x lives in x and y lives in y. So
you put indices. Like,
yeah, maybe we should just leave it the way it was. So if x, if the phi of x belongs is equal to y, and x is an x and y is an y. Okay. And phi is a map only. Okay, like that. Okay, sorry, that's the problem of not preparing something at all and improvising. Is it clear what I'm doing? Okay.
Yes, I think it's very clear.
All right, so. Well, let me just, since we're doing this, let me improvise even more and just say, so what is the Möbius band? So you can see better what the Klein bottle is. So the Möbius band is the following. You take a rectangle and you identify this side. You glue this side with this side, like this. And then now the boundary is this gray part here. It's where you don't glue. Okay, so now what you want to do is you want to glue two of these guys together. So when you glue two of these guys, what happens is this. So you take two Möbius bands. and you want to glue them together. So actually, what I'm going to do is you can sort of, you take this and you rotate it. So when you rotate it, you actually have the same thing. But now, you really should think that this side here is this side here, and this side here is this side here. Okay, so maybe let me draw a different color. So this is the blue, and this is the blue. Okay, but the actual circle that we have is something that starts, goes along the, so I start from here, go along here, and then when I get to this point, I come here, and then I go here. Okay, so now when I glue in, so I glue the blue, and then I have to glue the gray with itself. Okay, so I glue the blue, and then when I glue the gray, what happens is that now I can just draw another rectangle where I'm identifying this whole thing with this whole thing. And now the red is the composition of the two reds. Originally, these are not identified. So these points here. No, this is wrong. Yes, so it's a little tricky. Well, let me not talk about this yet now. Let me prepare and talk about this. This is really going outside of the scope of today's lecture. I can maybe do it at the end after we've talked about what I want to talk about today. Okay. All right, so let me just do a remark, talking still about oriented manifolds, is that if X is orientable, which means it admits an orientation, then there are and connected then it admits exactly two orientations. Exactly two orientations. And that follows, just from the fact that every vector space admits exactly two orientations. Okay. So now let's talk about the orientation of the boundary. So all of this holds for manifolds with boundary. I didn't quite specify that the smooth manifold had boundary or not, but I guess with or without boundary. Having a boundary won't change anything here. But having a boundary is great, because if you have a boundary, then what I'm going to tell you is that we have an induced, maybe I can call this a proposition. If X is a manifold with a boundary, which is oriented, then the boundary of X inherits a natural orientation. Okay, so how do we prove this? Well, see that this is actually not something obvious at all. Like, if for example, for the Möbius band, for the Möbius strip, it's a non-example of the proposition, but it's interesting because the manifold itself is not orientable, but the boundary is S1, which is orientable. So yeah, this is interesting. Oh, and before this proposition, actually, I should say that I haven't quite defined it, but we can also talk about a zero-dimensional vector space being oriented, and a zero-dimensional manifold being oriented. So this is maybe another remark. that an orientation of the zero-dimensional vector space is a choice of sign. So a sign is a number either +1 or -1. And that's the same, that's going to induce what it means to have an orientation on a zero-dimensional manifold. So yeah, so a zero-dimensional manifold is a disjoint union of points. And the tangent space of a point is just a zero-dimensional tangent space. So yeah, an orientation of a zero-dimensional manifold is just a choice of sign for each point of the manifold. And you'll see why this makes sense. I wanted to make this remark because this proposition is also true even if X is a one-dimensional manifold with boundary. So the boundary of X will be a zero-dimensional manifold. And it'll have a natural orientation even in this way. So, proof. So first of all, we can choose, recall that the boundary, the tangent space to the boundary of X is a submanifold, it's a subbundle of the tangent bundle of X along the boundary of X. Right? I explained that last time. Let me draw a picture. So if I take a point on the boundary, then this is sort of tangent space to the boundary, and then the tangent space at that point to the manifold has the same dimension as the manifold itself. So this is the picture. Tx of the boundary is contained in Tx of X. Okay. So now what we can actually do is, well, this has codimension 1. So we can always, we can find a complementary space, which I'll call Nx of X. For X on the boundary of X. And in fact, we can write this as bundles. So as bundles, we can write Nx plus T of the tangent bundle to the boundary of X is the tangent bundle of X restricted to Dx. The only thing that you have to be a little careful with is that to actually say this as bundles, you have to make sure that there is a standard way of choosing this guy, or there is some way that's going to vary smoothly with X. Because if you have a codimension 1 subspace of another space, then you can always find a complement. But can you find a complement that's varying smoothly with respect to X? And that's maybe not so obvious, but it is true for vector bundles, at least locally. And you can do this globally for the whole boundary. And it's maybe not completely obvious, but one of the ways to see that, if this is not completely if it's not clear, one way that you can do this is you can choose a Riemannian metric. That's just an inner product on X, and you can let this real be the normal bundle. So it's the orthogonal complement of the tangent space of the boundary. Okay, and then because the Riemannian metric is smooth, you can basically prove that this guy varies smoothly. And now you can choose, I'm going to let Nx be a vector in Nx such that its norm is 1 and it points outwards. So it points outwards. It points like this. What does that mean? I mean, points outwards, we can actually say what that means more precisely. It just means that there exists a curve such that gamma 0 prime is equal to nx. So that gamma of 0 is x, and gamma 0 prime is nx. Okay. Well, to be completely precise, maybe if you don't assume that it has that it's in the normal bundle, you also, just pointing outwards, you also would want to assume that gamma of t is contained in the interior of x for every t less than 0. So it just means, there's a curve like this that goes from minus epsilon to 0, and you look, and this vector is a derivative at 0. But we're assuming that it is in the normal bundle and has norm 1. So we can always find this. So you can always find like a normal vector field along the boundary that points outwards using this construction. Okay? So basically, now this guy here is a basis of this normal bundle, which has dimension 1. And then because we have an orientation here, and we have this choice of nx here, that induces an orientation in this part. That's what I want to explain now. So now we can obtain an induced orientation on the tangent space to the boundary using this equation, star. So let me explain this, because we're going to do a similar process a few times. But so how does it work? It's basically the following thing. We say that a basis v1 through vn minus 1 of the tangent space of the boundary is oriented if, well, when you put the normal vector pointing outwards on the first coordinate, and then you put v1 through vn minus 1, this is an oriented basis of Txx. Okay? So because we have the concept of being an oriented basis in Txx, because x is oriented, then we can actually say which bases are oriented, which bases of the tangent space to the boundary are oriented. Okay? So this works, this is the definition. I guess if so, this makes sense if the dimension of x is bigger than or equal to 2, which is the same as the dimension of the boundary of x being at least 1. Let me give an example before talking about dimension 1, because which is actually the most important one. But like, say for example that you look at S2. You look at the ball, B3. It's a ball, and it inherits a natural orientation. It inherits a natural orientation from R3, just because it's an open set of R3. So if I take a point inside of the ball, its tangent space will be the whole R3, and R3 has a natural orientation. So E1, E2, E3. So this proposition is saying that, this is an example. Proposition is saying that if you look at the boundary of V3, that's going to inherit a natural orientation. So the boundary of V3 is S2. And what this is saying is that we have a natural orientation on S2. So how do we find this natural orientation? So S2, is just the sphere. I'm going to draw the same thing, but now I don't have the interior, obviously. I just have the shell. So if I take a point on the sphere, I have its tangent space. What's the orientation of this tangent space? Well, the orientation is the following. How do I find an oriented basis? First, I pick a normal vector field that points outward. So it has to point to the outside of the ball. This is my nx. And now if I pick a basis of the space, a basis of the tangent space, so I pick these two vectors, I need to know which order they come. If it's first this one and then this one, or if it's first this one and then this one. And how do I know? Well, I have to put nx as the first vector, and then I have to put v1, v2. In such a way that this is an oriented basis of B3, of the tangent space to B3. So I just look, so I'm in R3, I actually need this one to be V1 and this one to be V2. Yeah. So this one will be V1, this one will be V2.
Essa base é natural em que sentido? Porque tem duas escolhas aí, né? Você escolheu primeiro que aponta para fora e também a posição, né? Aí isso vai ser fácil.
So the basis itself, desculpa, eu não entendi. Quais foram as escolhas que eu fiz?
A escolha que aponta para fora e a ordem, né? Você vai colocar na primeira posição.
Sim. Essas duas escolhas são feitas, mas elas são, digamos, universais. Se você escolhesse o contrário, né? Você poderia fazer isso. Mas quando eu falo que é natural com essas duas escolhas. Então você faz essas duas escolhas que não são, digamos, que são escolhas que são feitas, mas você faz sempre, para todas as variedades.
Tá certo.
Tá.
No final das contas, na maioria das vezes, não vai depender da escolha que você...
Não, depende. Assim, se você, em vez de escolher o NX como sendo apontando para fora,
vai mudar a orientação, mas os resultados...
assim, o grosso dos resultados não vai mudar, mas alguma coisa de sinal pode mudar aqui e ali. Né? Então, isso é importante, você escolher uma e manter nessa convenção. É uma convenção. Muitas coisas com sinais, né, são convenções. Então, você escolhe uma convenção e você tem que ficar com ela. E acontece que, muitas vezes, se você olhar para livros diferentes, autores diferentes, eles escolhem convenções diferentes. E aí você pode ter uma diferença no sinal. Mas tudo bem, assim, desde que você escolha uma convenção e fique nela, né, você pode até fazer um erro de sinal, mas aí vai ser um erro. E como dizem, né, se você fizer um número par de erros de sinal, aí você... é como se não tivesse feito.
Eu acho que é mais fácil de entender isso em termos das cartas orientadas no bordo. Porque vai ter uma direção que é positiva.
Sim, mas é equivalente, né? Você diz, você olha para a carta... Você olha para a carta, né? E nessa carta, né, você pode pensar no espaço tangente justamente como sendo o próprio Rn. Não, então você está dentro de Hn, e você está num ponto aqui do hiperplano, e o espaço tangente nesse ponto é o próprio Rn, né? E você quer colocar esse vetor para baixo, né? O menos dxn, como na primeira coordenada, e aí o resto vai dar uma base, né? Vai dar uma base orientada de Rn. Bom. Você pode fazer assim também, né? Mas esse cara daqui, na verdade, não necessariamente vai ser orientado da forma que está. Você vai precisar, talvez, trocar o sinal aqui. A não ser que você mude a convenção, né? Eu não sei o que estava falando.
Yuri. O ponto é que tem uma direção óbvia separada.
Sim. Sim, exatamente, Mas essa direção óbvia você pode pensar direto com o vetor normal. O bom do normal é que, sim, o normal é um campo vetorial definido na variedade toda. Bom, em termos de orientação, você não precisa realmente falar sobre isso, mas... Tudo bem. Okay, did you understand how to get an induced orientation?
Yeah.
Okay, so now we just need to talk about the case of boundary being zero-dimensional, because that's maybe not that clear from that equation. So if the dimension of x is 1, then the dimension of the boundary is 0. And so then, with the normal bundle is actually the whole bundle. So then the normal bundle to the boundary, the normal bundle. Sorry, what am I saying? And I'm just calling it nx, not nx of x. Just nx. Yeah, sorry, this doesn't make sense to say nx of x, just nx. If anything, it would be nx of the boundary of x, but I'm not going to write that for now. Just nx. Okay, so nx plus the tangent space to the boundary is equal to the tangent space, the whole tangent space. But this guy is actually the zero thing, the zero space. It's okay, you can take the direct sum with the zero space, and it's going to be isomorphic to just nx. Like with a trivial, in a trivial way. So now, what does it mean to say, if you have a basis here, and you complete with a basis here to get a basis here? Well, the completion is the empty completion, because the basis of the trivial vector space is just the empty set. But what you can do, which is in a way basically the same, is you can look at this, you can try to complete a basis for Tx with an element of the basis, which is the empty set. So it's like doing nothing. And you can compare this. You can say, well, if I do nothing, do I get the oriented basis of this guy that comes from the orientation? And the answer can be yes or no. If the answer is yes, like this guy, the nx by itself has the orientation that comes from x, then you say that this point is positive. So if the orientations match, if nx and v match orientations, then you say that the sign of x is +1. And if they don't match, then you say that the sign of x is -1. So in other words, what this is trying to say is that when you take the direct sum with the trivial vector space, that doesn't affect the vector space, but it could affect the orientation. So if the trivial vector space has a negative orientation, then you change the orientation. This is a convention, but it kind of makes everything that we say for higher dimensional spaces also hold for the case of dimension 0 summands. Okay? So maybe let's do an example, because I think that's maybe what will clear this. So the example is, say that your manifold is the interval 0, 1. Okay, now 0, 1 has a natural orientation, again, as a subset of R. So given a point in 0, 1, so if x is a point in 0, 1, I can just think of d dt at the point x, the tangent space to 0, 1, which you can think of as R. So if this is your interval, oops, drawing something straight is a little hard. This is my interval, and I have a point that I always take the orientation pointing, I take this orientation given by R. Okay, so this is the basis that is positive, and then if I take the other direction, it's negative. So what is the boundary of the interval 0, 1? Well, the boundary is the union of 2 points. It's the union of, it's 1, it's 0 union 1. So this is a 0 manifold with 2 connected components. Okay. So now I can see what is the induced orientation on this manifold. So this manifold, well, to do that, I have to look at the normal vector field. So I mean, the normal vector field is just 2 normal vectors. So here I have an outward normal vector, and here I have another outward normal vector. And all that I do is I compare the outward normal vector with the orientation coming from x. So when I am at this point, the orientation coming from x points in the same direction as the outward normal vector. And when I'm at this point, the orientation coming from x points in the opposite direction. So this means that the induced orientation on 0 is -1, and the induced orientation on 1 is +1. Okay, so then we write that the boundary of 0, 1, you can write it like this. So it's the 1 union with -0. Oftentimes, if you have an oriented manifold, you can put a negative sign in front of it to say that it's the same manifold with the opposite orientation. Okay. But since these are just points, people just often simplify this notation and they put a minus. But when you take a minus of 2 manifolds, you really are taking the union with the opposite orientation of the second one. This is just a convention. Okay, any questions about this?
Eu tenho uma pergunta.
Sim.
Mas acho que ela parece um pouco boba, na verdade.
Às vezes essas questões de orientações tem muita coisa que parece boa, mas que é realmente importante.
Por causa da classificação das variedades de dimensão 1, esse exemplo é praticamente a única coisa que é praticamente o único exemplo que tem daquilo que você estava falando antes.
De variedades compactas, sim. Né? Mas você pode, por exemplo, ter um caso que não é compacto, que é, por exemplo, quando você tem 0, 1 fechado, né? Quando é fechado num lugar e aberto no outro.
Ah, entendi.
Então, nesse caso aqui, o bordo é só 1. Né?
Aí você coloca mais ou menos o...
Não, aqui vai ser mais, e se você tiver, por exemplo, se o x fosse 0, 1 assim, daí o bordo seria só o 0, menos 0. Claro, assumindo que a orientação é a orientação induzida de R.
Sim.
E uma coisa que é óbvia também, something that's also kind of obvious, is if you switch the orientation on X, then you switch the orientation on the boundary.
Pode fazer um exemplo com um cilindro, com bordo, que aí acho que fica mais claro para mim.
Okay, sure. Let's do this example. That's good. So if we have the cylinder, first we need to orient the cylinder, and then we will get an orientation. So the cylinder, let's call this, there are 2 circles, circle A and circle B, and the boundary of the cylinder is the union of A and B. Okay. And now I want to orient, I want to find the induced orientation on A and B. This is a very good example, actually. Quem que perguntou? Eu não peguei o nome.
Foi o Renato.
Renato, valeu, Renato. Okay, so first we have to fix an orientation of the cylinder, and there is no natural orientation just as a subset of R3. Right, if I have a surface on R3, there is no natural orientation. There's only a natural orientation if you pick a normal vector to the surface, because then you can do the same as before. You can put the normal vector first. Okay, so given the cylinder, we really have to choose one orientation. But choosing an orientation is the equivalent to choosing a normal vector field, or just a normal at one point. So if we choose the normal like this, so if you think of the cylinder as sort of the boundary of the solid cylinder, then there is a natural orientation. So sort of this guy, and this guy, and this is V1, and this is V2. Okay, so in this order, 1, 2, 3. So now you can this will induce an orientation on A, and I'm going to draw the orientation. So how do you do that? So first you take a point in A, and you have to choose a normal vector field that's contained in the tangent space to C. So there's just one unit normal vector that points outwards. And at B, the unit tangent vector, the unit normal vector that points outwards points like that. So that means that the induced orientation on the top circle, so first you put the normal, and then you put the vector, so it has to be this guy. So the induced orientation goes like this. And on B, the induced orientation has to give the same orientation as V1, V2. So when you come down here, if you want to have the same orientation, then you have to rotate the other way. Okay? So there you go.
So are you saying that the orientation of A is different from orientation of B?
Yeah. Yeah. Another way to say this, to be to do something, maybe that's kind of what you want to see. You can think of C as the product of the interval with S1, right? The interval 0, 1 with S1. And if you have a product of two manifolds, then and each of the two has an orientation, and the product has an induced orientation. This is actually some observation that I wanted to say, is that if X and Y are manifolds, at most one of them with boundary, but let's say, yeah, so with boundary, but the second one has no boundary. It could also be the opposite. You could just pick the first one to not have boundary. And they are oriented, then the product has a natural orientation. And the orientation is given by the following equation. The tangent space to a point xy in x times y is isomorphic. It's naturally identified with the product or the direct sum of the tangent space at x to x and the tangent space at y to y. Okay, and then this equation, this direct sum, gives an orientation on this product. In other words, let me write this one more time, but I guess I'm going to stop writing this. If this is an oriented basis of Txx, and W1 through Wm is an oriented basis of Tyy, then V1 through Vn, W1 through Wm is an oriented basis of Txy of x times y. To be very precise, these vectors V1 through Vn, they're not quite vectors here. There's an injection that goes from the tangent space of x to the tangent space of x times y, and similarly for Tyy. They have to kind of inject these guys in here and inject these guys in here. Okay, but this is just the notation to get a little heavy. But the point is that if you have a direct sum, if you have an equation of vector spaces with direct sums, and all of the vector spaces in this equation are oriented except for one, that equation induces an orientation on this last one. Basically, in this way, like a direct sum, and this is an equation or an isomorphism. If you pick a basis on on all the summons, that gives a basis on the whole thing. And if you have orientations on all of these vector spaces except for one, this induces an orientation on the last one. Okay. So what does that mean for our cylinder? Let's go back to our cylinder. So for the cylinder, then we have a natural orientation, and it just comes from doing 0, 1, the orientation of R, and then the orientation of S1. So it's here, if you take this guy here, we can think of the C as the product of the circle, and where my circle is like this, 0, 1 with a circle. And you see that the orientation that I chose here in blue is exactly the induced orientation from the product. So on the first param, and my 0, 1 is vertical. 0, 1. Okay, so the first vector is V1 coming from 0, 1, and the second vector is coming from the orientation of S1. So that orients my C. And what is the boundary of C? Well, the boundary of C is going to be 1 times S1 union 0 times S1. This is what I called A, and this is what I called B. And then now is maybe what Renato really wanted to hear, which is, I mean, these two sets, these two boundaries, they have natural orientations just coming from S1. They're naturally isomorphic to S1. And the orientation is just, it's coming from the natural diffeomorphism. But what you should see is that the A, when you look at the induced orientation on A, this is the same as the natural orientation on A, just coming from S1 times 1. But B actually has the opposite orientation. So we can basically write that this is 1 times S1. So this is as sets. But as manifolds, as oriented manifolds, you can write this as union with minus 0 times S1. Okay. Is that what you wanted to know, Renato?
Yeah.
Okay. So this is one dimension higher than just taking the boundary of the interval 0, 1. But actually, this is a basic example of what I wanted to say next, which is what happens. So if X is an oriented manifold without boundary, and I consider the product of the interval with X. The claim is that, well, this, if you call, I can call X1 1 times X, and X0 0 times X. So these two manifolds have induced manifolds from the obvious diffeomorphisms to X. So these have induced orientations from the obvious diffeomorphism, diffeomorphisms with X, or just from being a product. Yeah, they are products of a point and X, so they have an induced orientation just from the product. Where a point, when you just write a point, you kind of take it with the positive orientation. Okay. Then the boundary of 0, 1 times X is going to be X1 minus X0. Okay, and why is that? Well, it's a very similar proof, or a very similar calculation to here. Basically, what's an oriented basis here? An oriented basis here is going to be ddt, and then an oriented basis of X. But if you are at a point 1x, then you have this guy at 1x, and then this is an oriented basis of txx. And the point is that ddt at 1x is going to point outwards. So this points outwards. And, it means, you can choose either that, or you can choose a metric so that this is normal, but that doesn't, that's not, you really only need to take a vector that points outwards. It doesn't even need to be normal or have norm 1. It will give you the same orientation. So this means that, if I pick an oriented basis like this, and I take this guy, the orientation that it induces, this induces the positive or the same well, let me say this again. So if you pick a normal vector field, for example, ddt at the point 1x, and you complete with an oriented basis of txx, then this is an oriented basis of the tangent space to 0, 1 times x. So this is an oriented basis of 0, 1 times x. So this x1 actually it has the same orientation as part of the boundary of x. So being part of the boundary of x will induce the same orientation that x1 naturally has. But on the other hand, if I take ddt, if I take the normal vector field pointing outwards at 0x, that's basically minus ddt at 0x. And then I complete this with a basis of txx. This is not an oriented basis of 0, 1 x. Okay, so that means if I want an oriented basis of 0, 1 x times x, I have to change this one. So that means that the orientation of x0 as part of the boundary is the opposite. The orientation of x0 as part of the boundary, sorry, not part of the boundary of x, part of the boundary of 0, 1 times x is the opposite of its natural orientation as a product, right? Its natural orientation. Okay, is this clear? It's a bit of a convoluted argument, but it's something very simple if you really understand, but it's maybe a little hard to write. Okay, any questions? Não.
Apenas um comentário, Vinícius.
Sim.
Que eu acho que da primeira vez que eu vi me deixou muito confusa, que tipo assim, mesmo que você tenha, digamos assim, uma variedade não orientável, mas o fibrado tangente, ele sempre é orientável, né? Vamos dizer assim, ele com variedade, né?
O fibrado tangente como variedade é orientável, mas ele como fibrado vetorial não necessariamente.
Isso. Exatamente. Mesmo que, vamos dizer assim, a base não seja orientável, mas ele como variedade sempre é, né? Que é uma coisa bem... É bem estranho isso.
Porque você está olhando... você está pensando... quando você pensa numa orientação do fibrado tangente como variedade, na verdade, está pensando numa orientação do tangente do fibrado tangente, né?
Isso.
Isso é um comentário interessante, né? Eu acredito que não deve ser difícil de provar.
Usando as cartas tem cartas com o dobro de variáveis e metade das variáveis é induzida pelas primeiras.
Você pega... exatamente, você pega...
Vai trocar o sinal das duas.
Você olha em coordenadas locais, e aí você mostra que quando você fizer uma mudança de coordenadas, mesmo uma mudança de coordenadas que tem um determinante negativo, vai ser basicamente o produto de duas transformações com determinante negativo. Então vai dar um determinante positivo. It's something kind of canonical in a way. You have twice as many dimensions, and when you can use any chart to define the orientation. And when you change the chart, even with a negative determinant, you're also going to have to change the chart on the tangent space, and it changes with the same sign. So the product will have positive sign. I think that's the proof. É um exemplo interessante. Okay. Other questions? Okay, so now let's talk about how the orientation affects transversality. So I guess this is the proposition, which is let X and Y manifolds and Y and W a submanifold of Y, and such that the boundary of W and the boundary of Y are empty. And let F be a smooth function, which is transverse to W, and the boundary is transverse. So now suppose X, Y, and W are oriented. Then the preimage of W inherits a natural orientation. Okay, so this is, the spirit of this proposition is the same as before, but I think it's instructive to actually prove it with you guys. Okay, so let's call n the dimension of X, m the dimension of Y, and k the dimension of W. So we know that Q is an n minus m plus k dimensional manifold. Okay, a submanifold. Of X. Okay, so the codimension of Q is the same as the codimension of W. Okay. And then now, and the other thing that we know is that what happens when you look at the derivative of F at Txq? Well, this is going to have to be contained in T f of X W. Okay, because F takes Q to W. So when you linearize it on the tangent space of Q, it has to fall into the tangent space of W. So it's something I didn't say last time, but it's obvious from the definition. Okay. In the case where W is just a point, then this is saying that the derivative, that this tangent space is contained in the kernel of the F. But it's actually equal to the kernel. So when you take the preimage of a regular value, the tangent space of this preimage is actually equal to the kernel of the F, as you know. Okay, so here it's not the kernel, but it's contained in the tangent space to W. And now, as we did for the boundary, we can, anytime we have a submanifold, we can look at the normal bundle. So there is something I'm going to call nx of q. So this is the normal bundle. So I'm going to just skip. I mean, you can take any complementary bundle, but I might as well just pick a Riemannian metric and pick the normal bundle and do something. It's not canonical, but it's fine. So the normal bundle has a property that it is a complement. So when you add, this is inside of Tx x. Okay, so the orthogonal complement of Q inside of Txx, that's a subbundle, or the subspace of dimension m minus k. So I guess I should say this has dimension m minus k. It's the opposite of the dimension of, the complement of the dimension of Q. Okay. And it's, it has the property that the direct sum with the tangent space to Q is equal to the tangent space to X. Okay. So now we can apply df to this. We apply df to this equation and we use the transversality equation. So we know that df of Txx plus T of f of x w equals T of f of x y. So this is the transversality condition, that the tangent space of x, when you push it forward by df, together with the tangent space of w, this spans the whole tangent space of y. So when you apply df to this equation, what you get is you get Tfx of the normal bundle. And then you have this the part that the part where you push forward the tangent space of Q. But because the tangent space of Q is taken to the tangent space of W, this is going to be contained in this part. So you might as well not write it in the sum, because this is what is spanning. So we actually can span the whole thing by just taking the push forward of the normal bundle. Okay, is that clear? So this implies this, because of this equation, because the f of t of the tangent space to Q is contained in the tangent space to W. Okay, so we have these two vector spaces that span this vector space, and now we look at the dimensions. So this guy has dimension m minus k. This guy has dimension k, and this guy has dimension m. So this is great. So what does that mean? That means that there is no way that these two spaces can, sorry, this guy has dimension at most m minus k. We don't know that df is injective yet. So the dimension of the image is at most the dimension of the domain. This has dimension less than or equal to m minus k. This has dimension k, and this has dimension m. So what does this mean? The first thing, it means that this has to be a direct sum, and this df has to be injective here. So df restricted to nq is injective. The dimension of the image has to be equal to the dimension of the domain. Okay, and then this has to be a direct sum, so they can't intersect non-trivially. Otherwise, they would not be able to span something of dimension m. Okay, so this is injective, and we have this beautiful. Let me just draw the direct sum as a consequence. And they actually don't intersect. I mean, they intersect just at 0. They don't intersect non-trivially. Okay, so we have this direct sum. So now using this direct sum, as I said before, since this one is oriented and this one is oriented, that induces an orientation on this one. So induced orientation. I mean, let me write this one more time if I haven't written enough. But so again, how do we, if V1 through Vn minus k, this is an oriented basis of nxk. So that's the definition. If when you apply dfx of v1, dfx of vm minus k, and then w1, wk, this is an oriented basis of the tangent space 2I for every, which is the same as saying for some oriented basis w1, wk of the tangent space to w. Okay, so using this direct sum, we can orient the normal bundle to Q. And now I'm not going to say it again. I'm not going to write this again. Using this direct sum, the direct sum that since this one is oriented, the normal bundle is oriented, and this tangent space to X is oriented, then we get an orientation here. Okay. Is that clear?
Yes.
Okay, so an exercise is the following. So if you look at the pre-image of W, this is an oriented manifold with boundary. I mean, everything that I said, doesn't care if you have a boundary or not. So if you look at the pre-image of W, it's a manifold that could have boundary. So if it does have boundary, you can look at the boundary of this, and we know that this is the same as when you look at the boundary of F and you take the pre-image of W. So this is something we proved last time. But the point is that as oriented manifolds, you're doing something different. Like here, you're looking at the induced orientation on the pre-image, and you take the boundary, and then you have an induced orientation. But here, if you restrict F to the boundary, then you can take the pre-image, and that has the induced orientation